Hello everyone. I hope you can hear me well. So yes, very good that Professor Peys already did the introduction for my talk, so I can be quite fast in that. So I will go more in detail about the carbonatable clinkers that Professor Peys was already talking about, although also a little bit different in chemistry than those. So yeah, the results I show, they are a bit of a collection from two European projects that have been already ongoing and a new project that we are starting also since last month. So yeah, okay, I can actually skip this completely maybe, but the point for making cement clinker is that you make minerals that are reactive to water, like the C3S, the C2S, and the aluminates and the ferrites that Professor Peys already showed. So you start from calcium carbonate and the silicon, and then a little bit of clays, a little bit of iron, and you want to have the reactive calcium silicates and a little bit of the aluminates and the ferrite phase. Well, if a cement researcher says ferrite, it's not the alpha iron phase, but it's a calcium aluminate ferrate phase. And the reactions to produce a cement clinker is produced in a rotary furnace, as we saw before, usually around 1450 degrees, although that depends a bit on the factory. And it's some kind of a solid state, but liquid assisted solid state process. So you have your mineral transformations aided by a certain percentage of liquid. I think Professor Peys already mentioned that 25% of liquid phase is ideal, which we also notice in the lab. Now, in the cement industry, there is a lot of effort going towards lower CO2 technologies. Okay, I just put two large cement companies' roadmaps on the slide here. So both for Holcim and for Heidelberg or for other cement companies, they really focus their research on trying to go for zero CO2 emissions by 2050. Okay, not so different from the steel industry maybe, which you know better. Yeah, popular topics in this regard are producing or using a lot of supplementary cementitious materials. These are just materials that can partially replace this clinker, which is produced at high temperature, or carbon capture and storage, or mineral carbonation. That's also things they often focus on. And it's this mineral carbonation part where I will talk about today. So if you do mineral carbonation, you will not have a cement which reacts with water, but you will have minerals that react with CO2. And yeah, these are still calcium silicates or calcium magnesium silicates. You make them react with CO2 and you form your calcium carbonates, which are the binder. It's not something that is just a researcher's dream, but you see here some advertisement of Belgian companies that are producing these materials via carbonation already. And we have some facade brick production based on the technology, and we also have some structural blocks being produced like that. Yeah, a bit more in detail about the principle. What are the reactions actually that are occurring? So you have your calcium silicate minerals. You shape them into this kind of product with some moisture. Then you introduce CO2 in a certain reactor. The CO2 goes into the pore solution, and then this also acidifies the pore solution a bit, which make these calcium silicates dissolve a bit. You have your calcium as well in the pore solution then, and then you have your carbonates and your calcium together, which can precipitate the calcium carbonates, similar for magnesium. And then that can grow your microstructure into something that is hard. What is important to make that reaction go well? It's a CO2 concentration to dissolve your CO2 in the pore solution and make the reaction ongoing. It's also the solubility of minerals and a whole couple of other parameters as well. And it's the solubility of minerals that is important for the rest of my talk. That's why I highlight it here. And this is actually where the importance lies for the carbonatable clinkers as well. Because this process tries to make phases that are reactive and that can dissolve well in this pore solution and that can provide your carbonates. In terms of process, it's completely the same as a Portland clinker process. So you also want to have a little bit of liquid phase and make your phases that are reactive. Now, not just with water, but with the CO2. And maybe now I will go slightly different from what Professor Peys has been explaining. The more traditional carbonatable clinkers that have been produced by Solidia, for instance, those were based on rankinite and wollastonite, but the ones that we are more investigating more recently are more the B-lite type, the C2S based clinkers, or calcium-magnesium based clinkers. We see that the reactivity for carbonation of the wollastonite is rather low, especially compared to the other calcium silicates. Which means if you add a little bit more calcium, okay, you need more calcium carbonate, but you gain it in the carbonation process further. So the more calcium carbonate you put, actually you can, more than the extra you put, you can store afterwards if you go towards the C2S. Now this calcium-magnesium silicate, that's a little bit more special. That's when you start from magnesium silicates, which are very hard to carbonate. Then you add some calcium, then this phase is the first one you can actually carbonate quite efficiently. So then you basically have two families of carbonatable clinkers that I will talk about today. And that's the C2S based clinkers, where there's still a little bit of rankinite can be in there. And that's the calcium-magnesium silicate clinkers, or Ackermannitic clinkers, we also call them sometimes, because this is the mineral phase called Ackermannite. Now, what is the status of these clinkers? So you see, we have the same friends in Poland as Professor Peys, but they do very nice work in upscaling in their rotary furnace. So these calcium silicate clinkers we have brought to TRL 7 in the Carbon for Minerals project, where we really went for a production of a ton of clinker and then afterwards made the construction products via carbon. Yes. In another project, these new calcium-magnesium silicate clinkers, that was more basic research, and we just went to TRL 5. We made like 100 kilogram of the clinker, and then we made some construction products as a prototype. So that's that's the status of that. But I mostly want to talk about how we used the thermodynamic modeling to optimize or to do a pre-screening of these materials. I'm not going to claim I'm a very big expert in thermodynamics. I'm more a user and using the softwares for initial screenings. So I hope you can forgive me for some basics. But what we did in the beginning of these developments of the calcium-magnesium silicate clinkers is we were actually working on magnesium silicate materials, like this slag, for instance. This is mostly a very silica-rich slag with a lot of magnesium and also a little bit of iron in there, which we couldn't carbonate, so we tried to modify the slag to make it more carbonatable. You see, we did some equilibrium calculations with a constant composition, but also did it with different calcium contents. We screened different temperatures, and then did it again for more calcium. And then with increasing calcium addition, we can see that the phase composition changed, of course. This is just the simulations at 1100 degrees, because afterwards we saw that this one was the one that corresponded the best with the XRD results of the clinkers that we made, of the slags that we made. Here it was still slags. So you can see that we go from a very pyroxene-rich material. You see enstatite, that's the magnesium silicate pyroxene. You go towards more the diopside, calcium magnesium silicate pyroxene mineral, towards the acarbonate, which is this composition. And we noticed when we made some compacts and we carbonated them, that the different compositions, we made some with 0 addition, we made some with 10% addition of calcium, 20% addition, 30% addition. We started from a strength of 0 megapascal, but we went up to 40 megapascal with this highest addition of calcium. And we noticed in the characterization that it was because of the presence of this acarbonate that these are the XRD results of the real ones. So you can see, well, the simulations worked quite well for the system. And we actually noticed also by characterization of the materials after carbonation, it's the acarbonate that completely reacts and gives the strength to our material. So this was the first point. We discovered that the acarbonate was very reactive. We were not completely happy yet, because we still had a lot of phases that are not carbonatable in here. So you see, the acarbonate was reactive. Okay, very good. It gave us strength, but it's a bit a waste of energy to make a clinker with only 18% of a reactive component. There's also forsterite here. There's still some diopside, which don't react at all. So then we went to maximize completely the acarbonate content. We started here from the same slag. And what was our strategy now? We want to oxidize the iron oxide. You see there's still quite some iron oxide. So to take it away from the forsterite, and then we have some additional magnesium, we have some additional silicon. If we then also put additional calcium, we can further maximize this acarbonate. We just put on, instead of a fixed composition, also a fixed oxygen content, we now fixed the PO2 of the simulations to something which looks like a cement kiln. And then we ended up with these simulations. With the calcium additions, your mass now drops because the CO2 goes out. And then you can see something quite similar happening as before, but now without this forsterite. Instead, we have a little bit of the magnetite, spinel magnetite. And now we can actually go here, if we add 40 weight%, 45 weight% of calcium carbonate, we can go to systems with 70, 80% of acarbonate. And then, we make again the compact, we carbonate it, and then we go to strengths of around 80 megapascal, with which we were quite happy. And so these are the formulations we further worked with also in this upscaling and this production of the pavers that you saw before. Then there was still a little detail which we could fine-tune, and that is then the acarbonate composition. It's still we could fine-tune the reactivity of the acarbonate by pushing away the aluminium from it. And this we did in a few different ways, but it's for instance, if you add a little bit of alkalis, then you form a little bit of nepheline and you drag your aluminium from the acarbonate, which makes the solid solution with galanite a bit less, and then it makes the acarbonate more reactive. Yeah, and then we could increase the strength even a little bit further towards the 100 megapascal. Yeah. On small paste compacts, to be clear, and so that it's the region where you, if you would make a paste compact of an OPC, that's quite similar as that, I think. Okay, that was the main part of my presentation, the new calcium magnesium silicate clinkers. But we also had some work on the calcium silicate clinkers, mostly toward this B-light, this C2S, where we use as input also secondary materials, mostly recycled concrete fines or steel slags, because they also already contain a lot of calcium silicates. And that's what we also did in this Carbon for Minerals project. And why I also wanted to show this is that it's not always as straightforward as adding calcium carbonate to increase your carbonation reactivity. If we work with BOF slags, you actually have to go the other way, because your reactivity or your strength after carbonation comes from calcium silicates. And then the decalcium silicates, and not from free lime as you would have in a BOF slag. We actually have to add some silica to increase the decalcium silicate content. Yeah, so we have this maximum calcium silicate content between 10 and 14 gram of silica addition. And yeah, maybe something else. We also track the amount of melt which is formed at a certain temperature, because yeah, first, practically it's very nice if you don't melt down your material if you are working with platinum crucibles. But also, yeah, in industry, you would target some 20-25 weight% of melt in your kiln, and if it happens in a wide temperature range, that's also quite nice. So you see here, for instance, the 20-25 weight% has quite a big temperature window. Here, it's, there's 100 degrees between these points, and so that's quite well manageable in a kiln. Yeah, that was about it. So now we also have a new project where GTT themselves are involved, so I wanted to say something about that as well. And here we work on new types of steel slags, or it's mostly on electric arc furnace slags. So because of the trends in the steel sector, we will not have blast furnace slags anymore, which is quite dramatic for the cement industry. So we have to learn how to deal with the electric arc furnace slags. And so we will study the optimization of these slags for carbonation processes and check the reactivity with CO2, but also check how we can optimize the environmental quality of the slag and of the carbonated materials afterwards. And yeah, so, and also GTT will do some work in optimizing the modeling of several steps in these processes. Yeah, so that's about it. Thank you for your attention. If there are any questions, you can ask me, and yeah.